In this video, we'll tackle problem number 1 from the Sinusoidal SHM problem-solving worksheet. Problem number 1 reads, the springs of a 1,500 kilogram car compress 5.0 millimeters when a 68 kilogram driver gets into the driver's seat. If the car goes over a bump, what will be the frequency of vibrations? So what we're interested in solving for here, what they're asking us to solve for, is the frequency at which the mass on spring system, the car on its suspension, will vibrate. Frequency is 1 over 2 pi times the square root of k over m. Now, in this particular problem, we don't have the k value. We have the mass of the car and driver combined together, 1,568 kilograms. That would be our mass here. But we can't solve for the frequency because we don't know the k value. So step number 1 for this problem is going to be to solve for the k value. So step number 1, solve for k value of car springs. Okay, so to do that, we have to think about this in these terms. We have to think about the car as being a mass on a spring. And here is our 1,500 kilogram car on its springs. Now, it tells us the driver gets into the driver's seat, okay? And when he does that, he compresses the springs by 5 millimeters. So if this is the car's normal equilibrium position, then when the driver gets in, the car compresses, okay? The car goes further down. This is still our 1,500 kilogram car. The reason why the car moves in the downward direction to this new equilibrium position, so this would be new equilibrium position, is because the 68 kilogram driver sits on top. 68 kilogram driver gets on top. That causes the whole car to settle lower. The car is moving downward. What force is causing this displacement, this change from one equilibrium position to a new equilibrium position? Well, it's the force of this mass being added. In other words, the weight force of the driver pushes the spring down further, compresses it further than where it started from. So the way that we're going to look at this is we're going to say that the increase in spring force as the car is compressed by the driver is going to be equal to the force applied by the driver. So in other words, to go from one equilibrium position to a new equilibrium position, we're going to say that there was an increase in spring force related to this displacement. So we know that the mass of the driver is 68 kilograms. We don't know the k value of the spring, but we do know that the change in position of the spring was 0.005 meters, or 5 millimeters. And we know that we're here on Earth, or we can presume that we are. So G will be 9.8 meters per second squared. So how are we going to use this information to solve for K? I'm going to write a sum of forces for the movement along a vertical axis. And we'll call this negative x and positive x. So this is our x-axis. So we're having negative downward displacement. So the sum of forces in the x direction is going to be equal to the upward spring force, which would be negative kx, minus the downward weight force of the driver, which would be the mass of the driver times g, and that is going to be equal to 0, because at the new equilibrium position, the car stops. It's not going to oscillate around. We're going to lower the car down and be at an acceleration of 0. So our forces, when summed together, equal 0. So negative kx is equal to mdg. I just add mdg, the mass of the driver, times g, the weight force of the driver, to both sides. Now I'm going to solve for k. K will be equal to negative mdg divided by x. And for our particular problem, that means that k is going to be equal to minus 68 kilogram driver times 9.8 meters per second squared divided by our displacement. Now our displacement is in the downward negative direction, so it's negative 0.005 meters. Now we're ready to plug this into our calculator. When we plug this into our calculator, we're going to come out with k is going to be equal to 133,280 Newton meters. So that is our k value. But that's not what we're solving for. We want to solve for the frequency. So now the step number 2, solve for frequency. So the frequency is going to be equal to 1 over 2 pi times the square root of k over m. We know k and we know m. Now in this case, the car goes over a bump while the driver is in it. So that means the mass for this problem, this mass right here, is total mass, which is going to be equal to 1,568 kilograms. So our frequency of oscillation will be 1 over 2 pi times the square root of 133,280 Newton meters divided by the total mass of the vehicle and driver, 1,568 kilograms. We can run that through the calculator, and when we run that through the calculator, we come up with 1.47 hertz as our final frequency. And this is our final answer to problem number 1. I hope you found this explanation and solution helpful.